C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovid's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
Alrighty, good day, folks. Welcome to our webinar. Just a few housekeeping items before we get started here. Today's session will be recorded and available for playback at the end of today's event. For some reason, if you have to drop off, or if there are folks that weren't able to make the live session, you will be able to catch up on what was discussed. I'll also make reference to our Q&A feature. If you do have any questions throughout today's session, please feel free to message those through. It's on the bottom right side of your screen, I believe. So we will be reserving some time at the end of the formal session to go through a Q&A together. All right, that being said, we're about, top of the hour here, so we'll go ahead and jump into it. Welcome everyone to today's webinar. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And today we'll be looking at the thermal conductivity of polymer composites, taking a look at some of the different approaches for measurement, as well as some different application examples. So I'll start with a quick introduction to C-Therm, for those that may be new to us, who we are, what we do. So C-Therm Technologies, we are a scientific instrumentation company focusing on the measurement of thermal conductivity. Really, we are experts in the transient class of measurement, and this is what we'll be featuring quite heavily in today's session. So, as we go through here, we'll be really looking at that thermal aspect across polymer composites research. And what we will be, focusing on are some of these transient methods that are available on our flagship instrument called Trident. So Trident here, we can see this is our modular system, which brings together 4 different methods for thermal conductivity testing. Really, when we look at the variety of sample types, the conditions that groups are interested in testing under, there's no one-size-fits-all solution. So with Trident, it gives you the options to really pick and choose the best tool for the task at hand. And this quote here really embodies that idea. This is one from Abraham Maslow: when all you have is a hammer, everything looks like a nail. And again, really what we typically end up seeing is one of the, let's say, sources of bad data is when you take a good method but apply it in a scenario it just really wasn't designed for. So again, today we'll try to go over some different sample types, different testing conditions, and demonstrate why certain methods are more applicable than others, and how we can use this to get the best possible data for the research interests of relevance. I will also just take a moment to mention the fact that while C-Therm, we focus on thermal conductivity, we are partnered with both Rigaku and Metrovib for North America for their line of thermal analysis, so DSC, STA, TMA, as well as DMA instrumentation, respectively. So while today's session will be heavily focused on conductivity, thermal conductivity, if you did have interests in other material characterization needs, this is something we're certainly happy to assist with. Lastly, I'll make note of our contract testing division, Thermal Analysis Labs, or TAL. So all of the methods that we'll be discussing here today, the ones that are available on Trident, we also offer that as a contract testing services, as well as other methods that exist in industry. So our partner methods, as well as other options. So if you were looking for a group to do some testing for you, maybe you weren't quite ready to bring an instrument in-house, again, so just drop us a message there. We're certainly happy to discuss what those options would look like. And those of you that may be, let's say, new to thermal conductivity, or maybe folks that just want a refresher, we've had a method selection guide for many years now, but we actually just recently updated. So this is a freshly, I think just this past month was updated. So it's a guide that really goes over, all the methods that we offer on Trident, but then, of course, other methods in industry, talks a little bit more detail about where they're commonly applied, some considerations and things of that front. So This is a free resource if you're looking to maybe kind of get some more information and do a little digging on your own. This is a great tool to take advantage of. And lastly here, just kind of finishing out the introduction, we always like to end with a client testimonial, really to illustrate how folks are using our instrumentations, what value they're getting. And this one here I thought was quite relevant. So this one is from Praboda Bekon from the University of Connecticut, noting that the MTPS sensor, very easy and quick technique to measure the thermal conductivity of their samples. So in their lab, they use it for polymer and graphene materials. Having the sensor operate at a broad temperature range is a plus. And the team at C-Therm is also very helpful and responds quickly if we need any support or guidance to use the instrument. So, we do have a list of testimonials available on our website. If you wanted to hear what other folks have to say about their experience working with us or using our instrumentation, definitely feel free to check that out. All right, but that being said, let's really now go into the bulk of today's session. Of course, talking about polymer composites, let's address what they are. So, at a very high level here, polymer composites, these are materials that, we're taking a polymer and then combining it with some other materials, whether that's a reinforcing agent, like different fibers. This could be carbon fiber, glass, other polymer types, or fillers, such as, ceramics or metal particles, to name a few. Essentially, it's the combination of materials to achieve a specific tailored performance. And this can take many different forms, as we'll go through here today. Sometimes these are bulk materials, other times they're thin sample formats, non-solids even as well. So we'll get into that as we go through today's session. So I took a quick look back and just wanted to maybe flag for some of the folks that are from academic backgrounds here. In the past 5 years, where are we seeing, let's say, some more growing fields or more popular use cases of these type of polymer composite materials? So this was, kind of a study here from a few different publications, kind of collecting some of this data. But interestingly, one of the top hits was actually machine learning driven composite design and testing. So maybe not necessarily a specific type of polymer composite or application, but just how groups are addressing the research and going through different formulation R&D standpoints. So that was one interesting area, but these next three are really, I'd say, maybe a little bit more what we're going to focus on today, different types of polymer composites and how we test them. So one of the big ones was Vitromer-based smart composites. So these are essentially composite materials that could have properties like self-healing capabilities. We've seen some application of this. I remember seeing some papers on like hydrogel research where, after you introduce a tear and then it can, reseal together. So quite interesting. Another big one, and we see this across a variety of different applications, but sustainable and bio-based material composites. Of course, with the drive for renewable and reduced carbon footprint, these bio-based materials are still quite popular and definitely on the rise. And then lastly, I think this is a kind of a broad class that kind of got put together, but novel, functionally tailored composites. So, you could imagine this from anywhere from, things that can handle extreme conditions, high, low temperature. Also, of course, there's some aspects to consider on the mechanical structure for very specific use cases and things of that sort. But just some of the popular areas that we've seen, pop up in the research side. Now, for maybe folks that are not as academically interested, but more just, this is, your field of work. In industry, I think no surprise, the top three, I think most popular, I'd say, uses of these types of polymer composites are covering aerospace and defense, automotive and transportation, and renewable energy sectors. it looks like by the end of 2025, these three combined will be contributing over 65 billion to this market. So certainly quite a bit of work is currently being done in this space for sure. And we'll see how some of these different both research and industry-based applications are looking into the thermal behavior and the thermal properties of their materials to address certain considerations that are needed. So, when we're talking about composites, I kind of mentioned these points over the last couple slides, but the benefits that they introduce or provide, there's a variety of different viewpoints you can come at this, but some of the big ones is a really high strength to weight ratio, improving on that structural performance while lowering the weight. That's quite a big area. Again, you could imagine for the automotive or the aerospace industry, this is something that's quite relevant there. Tailored properties, of course, that's the whole point with these composites. It allows you to fine tune, whether that's the thermal, mechanical, electrical properties. These can be adjusted to meet your specific criteria of interest. And of course, some others here, like, improved thermal stability, endurance, dimensional stability. So, shrinkage or warping, addressing some of those considerations on that side. Now, we're talking about polymer composites. So I did just want to take a very quick moment here, again, quite high level, just to address when we're talking about heat transfer, because of course, this is the focus for us here today is the thermal and the heat side of things. In just a standard polymer, you can really envision this as, irrelevant to any additives or fillers, the polymer itself, how it conducts heat, and the ability or the strength of that material to transfer heat is often related to the level of organization or the crystallinity within that polymer chain. This is related to that mean free path for phonon transfer. And of course, different polymers, different even formation processes can impact this. But, again, for us, when we're looking at the composites, what's, I would say, more relevant and interesting here is how these different polymers interact with what we're adding to them. So for fillers, for example, in an example where maybe we're looking to increase that effective thermal conductivity while adding a conductive filler, what this is going to allow for is a network for improved heat transfer within that system. But of course, the type of filler, again, whether it's, a nanoparticle or a fiber, this can introduce different behaviors. How uniform are the fillers behaving? Are they really, orienting or aligning in the way that we're intending? These are different factors that we'll maybe take a look at here today with some different examples. So I want to start it with a, very, very basic example here, but this was some data that we had presented, I believe it was a few years ago with a company called Alteo. They have they focus on a variety of aluminum-based fillers. And, in a very simple scenario and I'd say like a research study, adding different amounts or increasing that filler loading, how is that going to impact your thermal properties? So again, a very straightforward data set here, but just looking at, the control. This was an epoxy-based resin that we tested and then added various loading levels of the Alteo filler. And, as you would typically expect, there's this net increase in thermal conductivity, increased heat dissipation up to a certain point, and then we maybe see some diminishing returns at the upper end. But, in a scenario like this where you're looking to, quickly quantify, especially like in an R&D scenario where you're maybe going through various formulation iterations, one of the really, I'd say, quickest and easiest ways to go about this is with the MTPS. In the scenario of this testing, the MTPS was actually the choice method for a variety of reasons. One being that the samples were quite small, about 18 millimeters in diameter. This is essentially the minimum size for MTPS testing. There are other methods that we'll talk about, but in terms of really getting away with some of the smallest sample formats, also inherently one of the quicker and easier methods to get set up and running with, the MTPS certainly had some advantages here, and all of this data was collected with this technique. Now, of course, this is just, obviously, we're introducing fillers, we're seeing that net increase, but you can also look at some other factors here. This is a publication from a couple of years ago looking at the impact of different functionalized multi-wall carbon nanotubes on the nanocomposite properties. So this was some interesting research coming out of Malaysia, again, using the MTPS, but while they were still looking at different loading levels of this filler, they're actually, on top of that, varying the specific type of filler. So at the same loading level, we're seeing different behavior, different net increases to thermal conductivity based on the functionalization that was used on that filler. And as we can see, again, the similar story, increasing that loading level, we're seeing generally this net increase in performance. But the thing to point out here is when we are looking to really optimize materials, if we're looking to hit a certain threshold of thermal conductivity, how is the best and most efficient way to get there? And we can see in this data set, actually at the 2% loading level with the U variant, it's actually outperformed by the 0.5% loading of the SD variant here. So just another example, when we're looking to optimize and really back some of this up with some testing here, we can really get away with using less material in some cases and achieving a similar or better thermal performance. So again, is this type of testing here, very early development R&D focused work. The MTPS utilized here again, kind of demonstrating it's really, I'd say, great fit in this space. Now, when we're adding or talking about fillers, one of the biggest issues that is typically present and something that we see, come up time and time again with different folks that we work with is what happens when that additive isn't behaving as it's supposed to. So whether that's through, let's say, agglomeration or sedimentation to one side of that polymer composite. What happens in this case? Well, from a material perspective, you can imagine if we are working with, let's say, a thermal interface material, this can result in uneven heat dissipation, hot spot buildup. That's a safety risk for things like thermal runaway, for example. But from a testing perspective, it's also something that we need to consider because depending on which method is used, this can introduce some, let's say, variability in your results. And the reason for this is depending on which technique is employed, each method will have its own set of underlying assumptions. Some methods are directionally dependent in their output, others are more of a geometrical average. The assessed volume of material can be different for different techniques. So we have to have a way to, really identify some of these issues to make sure that whichever method we do use to do that, let's say, final quantification of performance or certification, it can be done with confidence. And one way that we've really demonstrated a great way to detect some of these issues is with the MTPS in doing what we call thermal mapping. And what this is, essentially, if you have a material, so this is was an epoxy filled with a conductive metal nanoparticle, we can see, like just with this example, very obviously non-uniform. We have areas of high concentration of the filler, areas where basically it's just the neat polymer, very visibly obvious in this case. But the idea that we want to show here is that with the MTPS being a single-sided sensor, one of the nice advantages here is that we can actually place it at different locations across the surface of the material. And then very quickly, within about, start to finish, cool down time, data collection, about 60 seconds per spot, we can get some effective thermal conductivity values based and, again, quantify and relate them back to that filler dispersion. So we're showing here, the area in the top left, kind of over here, very little filler. It's coming in at one of the lower values compared to, the top right here, much more densely populated with that conductive additive, giving us a value almost 3 times higher. So all this is to show is if you have a material that maybe isn't as easily visibly detectable, maybe you're dealing with an opaque base, we can't just look at it and pick up on these issues. The MTPS can be a tool that allows you to very, early on and often assist with that iteration velocity. So as you're formulating, going through different stages of, product, iteration, you can pick up on some of these issues earlier on so they don't end up coming back to bite you later in that development cycle. So again, just one quick example here with the MTPS on that thermal mapping. So looking at like across the surface of your material. But we can also look at it in terms of the effect of sedimentation. I know for some groups that are dealing, that we've done work with in the potting compound industry, these are typically, encapsulating larger volumes of material. But when you have these kind of large systems, if that filler in that let's say uncured state isn't stable and it settles towards one side, this can again cause some issues. And how we can actually pick up on this is with the MTPS, again, single-sided, the depth to which we're measuring is a few millimeters into your sample. So by actually taking your sample coupon and placing, let's say, side A in contact and taking a measurement, and then flipping it and doing the other side, we can compare those results. And, ideally, they would be exactly the same, kind of indicating consistency throughout. Or if you're seeing something like this, where again, let's say the top side significantly lower than the bottom, we can infer that, all of that or a lot of that conductive filler has settled towards one side. So again, it's finding ways to utilize these different methods to demonstrate some property of your material, whether this is, again, for R&D, QA, QC applications. There's quite a bit of relevance here in terms of allowing sample optimization. And I wanted to share this here. This was a publication from a couple of years ago on, we're talking about some of the different, polymer composites out there. This was an epoxy resin, but a biocomposite. So again, kind of some of those bio-based materials here. And the interesting aspect of this study, so this is coming from some groups out of France, looking at essentially validating some of their computational and analytical models. So they were both producing and directly testing these biocomposites. So they're flax-based materials. They demonstrated some benefits. It's a low-cost raw material to be used in this type of application. They demonstrated improved structural strength, lower weight. Again, some of those points that we see brought up in terms of the benefits of composites. But essentially, what we are kind of going to show next is how they took some of this data, and they were, again, doing analytical computational studies, but it's really important to be able to validate those studies, right? So what they were actually doing is taking measurements of these biocomposites with the MTPS and comparing that to their simulated data. And as we can see here, in notes directly from the author here, very good agreement between the experimental and theoretical results. So as much as there is quite a bit of advancement in different types of simulation work and how that can help further advance research, there should always, of course, be a way to validate some of those models. And of course, the best way to do that is by directly measuring the materials of interest. So again, this was a really nice paper, really demonstrating the two different sides of this type of research, but how they can come together and be used to help validate those measurements. So I wanted to take a moment to talk about TIMS. I've kind of mentioned at the beginning, but TIMS is still quite a big area of research. So thermal interface materials, for those that are familiar, these are materials that are placed between a heat generating and a heat dissipation or cooling device. So, you could think inside of a computer, you have your CPU. It's going to heat up. So there's, that heat sink that's placed with the fan to dissipate the heat. But when we put those materials together, of course, when we look, they might look like they're making really good contact, but there's going to be microscopic air voids. And air is the biggest killer of heat transfer. It's quite insulative. So the thermal interface material, is essentially here to fill those gaps and improve the heat transfer between those components. Now, based on that aspect, thermal conductivity is going to be a very important performance metric. When we look at, technical data sheets, you'll typically see within the first, sometimes right at the very top or within the first 3 property measurements, you'll see the thermal conductivity value. And of course, this is, comes back to the idea of this is being tailored based on the filler or the additive involved. So when we talk about TIMs and technical data sheets especially, I wanted to bring up the Flex TPS. So this is one of the other methods that is available on Trident. So the transient plane source, when we're looking at methods that can really, are more commonly used to, quantify performance, certify values, again, reference on technical data sheets, the TPS is one that is quite commonly used. And an example of this was this was a silicone-based gap filler that we purchased, spec value of 2 watts per meter Kelvin using hot disk transient method. So hot disk or TPS or ISO 22007-2. It's all referring to this style of sensor right here. So spec at 2, wanted to, of course, when we talk about technical data sheets, trust but verify. So, we measured these well within the expected range. So definitely a good quality material here. But thought it'd be interesting to similarly test it with the MTPS. So, a question we get a lot is how do these different methods compare to each other? And as I was saying, some methods, there are certain levels of bias that can be introduced. So, how does that come up and to what extent, right? So in this sample here, again, I would say between the 2 results, they're both within that 2%, 2 watt per meter Kelvin range within 5 to 10%. So really good agreement here between the 2 different methods. But this good agreement is really only possible based on the fact that these samples they're well optimized and quite consistent. What happens when, again, we're not maybe necessarily to that point? So I want to come back to an example here, again, kind of the mapping with the MTPS. This was on again, a filled silicone adhesive here. We can tell just by looking at it, not perfectly uniform, and kind of showing that with different measurement locations with the MTPS, we're seeing quite a big range of values depending on the test location. So if we took a sample like this and then measured it with something, let's say like the TPS, which is double-sided, so we actually have to take the sample, cut it in half, put one piece on the top and bottom to do our test, what type of results would we get? So we did this actually, and we can see that the TPS result is somewhere in between the MTPS range. It's above the minimum value that was obtained, but definitely below the maximum. So the reason I wanted to share this is because when we're looking at the method of measurement, TPS here, double-sided. So we're actually, that heat pulse that's generated from the test is entering from the top and the bottom side. It's entering, it's not directionally dependent. So it's this kind of average value spread out over the area of assessment versus the MTPS, which is the localized measurement at where it is placed on the sample. So in terms of like which value is right and wrong here, well, they're both providing you an output of thermal conductivity. TPS is just simply averaging out that larger area, whereas the MTPS is more of that fine comb approach where we're picking up on some more localized differences. So, really in terms of the use of MTPS and TPS, together they are very synergistic. If you just had a TPS or some other method like LFA or some steady state techniques, the impact of that filler consistency might not always be readily apparent because again, some of these things can be averaged out or essentially masked from the output. Now, this can introduce, of course, some error depending on what we're looking at. Again, when you have uneven distribution, performance issues, etc. But the benefit of having MTPS and TPS together, for example, is again that pre-screening. All of that early on work can be done in a very effective manner with the single-sided MTPS. And then once you've gotten to that point where things have a certain level of consistency and you're confident where you've gotten it, then of course you can pivot to whichever method is most interesting for that final product certification. So again, they come together quite well and really help complement each other in these cases. The last kind of example on thermal interface materials I want to share was a case highlight from some work that we did in collaboration with a group called TESSA. So TESSA tapes, they have a line of thermally conductive self-adhesive tapes. And this essentially collaboration came about because they, of course, manufacture their own TIM materials. But what they were doing was some in situ performance comparisons against some of their competitor brands. And looking just at the technical data sheet values, the real world kind of results that they were getting based on how much heat was building up when these materials were placed in a system, it wasn't quite making sense. They were seeing some very high heat being generated with some of the competitor brands, although the technical data sheet says the thermal conductivity was such that it should be dissipating more. So essentially they came to us as a way to kind of a third party here to essentially validate some of these claims. We had tested two of their materials and found some pretty good agreement, actually even a little bit higher than what they were speccing using MTPS here. But overall, kind of it made sense from that side. But then when we actually tested the competitor brand sample, which was again spec'd at about 1.5 watts per meter Kelvin, our measurements were coming in about 0.44. So this was essentially confirming what they had been seeing in their in situ testing, but also kind of an example of why it's very important to really verify some of these technical data sheet claims. Although, the technical data sheet, does give us a baseline value here, they're not all created equal. There are certainly some technical data sheets that just kind of put a conductivity value. You don't really know what method was used, what were the conditions. Some will provide a method, but to a limited amount of additional information. There are some, however, that do provide, the method, the conditions, the compression. If it's a softer sample, was it compressed to a certain degree, because that can impact the results, things of that nature. So all this is to say, technical data sheets are kind of, I'd say the overarching message here is trust but verify. Okay, so kind of getting close to wrapping things up here, but I just wanted to talk about a couple, I'd say, more niche sample formats, and one of those being thin film polymer composites. So, thin films, these are applied across a variety of different applications. I have a couple on screen here, but, different like sensors, biomedical devices, energy, packaging, etc. But when we talk about thin films, oftentimes there's, a challenge here in how thin they are and what methods exist. All the data that we've talked about previously has been essentially on bulk size materials, or those that are, a few millimeters in thickness. So how do we deal with something that's, in the micron range? And to address that, I would say really the best option here is the TPS, so Transient Plane Source, specifically the dedicated thin films utility. So this method, this TPS sensor, there's a specific mode of operation that it's a little bit of a different setup. You can see there's essentially a layering procedure that's done with the testing. It actually uses the TPS with a conductive backing material and then introduces layers of the film for testing in a successive manner. But ultimately, it's going to be, I'd say, the most direct way to get at that thermal conductivity of your thin film materials. And I wanted to share just kind of briefly here, this is an example screen grab of the Trident software running a that had collected a thin films measurement. Just to give you an idea of what kind of this looks like. And overall quite straightforward here. Really, it's a 3 measurement process. And the only thing that we have to really be aware of is the thickness of the material that we're testing. So this is inputted here. You can see measurement number 1 is just kind of our control blank with just that conductive backing material, followed by 1 layer of your film and then a second layer up. And essentially we're building out a thickness dependent linear regression based on the temperature change that's observed. And all of this is used to determine and output our thermal conductivity. But essentially here, the point is if you are dealing with materials that are really below, I mean, if you're in that, 10, couple hundred micron range, thin films, really the TPS has a really nice fit there and can certainly provide a lot of value from that standpoint. The other, I'd say, interesting sample format to take a look at is on melt state. So this, polymer composites, polymers in general, often they are formed with some thermal process. So whether that's, like melting down and compression molding or some more advanced things like, ejection molding, 3D printing applications like additive manufacturing. But the thermal conductivity is important here because this can impact a variety of aspects of the end product. So how those, again, when we're talking about composites, how those fillers or materials are aligning or spreading within the sample. This can induce directional properties. When we're trying to optimize some of these systems, oftentimes you're doing some modeling, but again, as we kind of showed with that paper earlier, being able to back up some of those models with some real test data can be quite important, etc. So to address the measurement of a melt state polymer, again, how do we kind of go about that? And really what's the challenge here? Well, so the challenge is that we're dealing with something that's typically at a higher temperature, and depending on which sensor or method you're looking at, it can be quite an ordeal to clean up, or sometimes it can inherently damage the sensor in that like high temperature melted state. So to address this type of testing, really the guiding recommendation would be the use of the transient line source, or TLS. So the TLS, you can see here, it's a needle probe style sensor completely sheathed in stainless steel. The ASTM standard for polymers that the TLS conforms to is D5930. We have capabilities testing up to 300 C. And one of the other aspects we didn't really talk about much for the other methods, but for the TLS in particular here, there are high pressure testing options. So I know some of these, different injection molding systems, there's a certain temperature at which that molten polymer is held at, but it's also under a pressurized environment. So one of the really important things is being able to test under a representative condition. So again, there's some nice capabilities here. I just wanted to share a quick data set. So this was using the TLS. Essentially, the needle probe is inserted down into that molten polymer. So that's held in like a containment vessel or crucible in a thermal well or chamber. And then we can do testing, of course, across a variety of temperature ranges, against that in that molten state. So, I would say depending on the format that we're working with, traditional bulk materials, thin films, molten state materials, this really, as you can see, kind of dictates which method can be most appropriate. So, ultimately to summarize in today's session is polymer composites are, of course, the advancements that are going on in this space it's continuing to grow. Tailoring these properties is something I don't see slowing down anytime soon. But across a variety of different applications, thermal conductivity is a very important performance metric that has to be quantified. And, if this is a field of research that you're working in, these transient techniques, we had some examples here today, really provide a robust framework. They help speed up the measurement. They're quite rapid in terms of their output, and provide reliable test options for a variety of sample formats. So all that being said, wrapping up here, I'll go into a very quick outro. I've seen a few questions come in, actually more than a few, so we'll get to the Q&A section here in a few minutes. But just as a note, if this content was of interest, or maybe you're looking to gain some additional resources, past webinars and the different papers that we'll reference, this is all available on our website. You can find links to these www.ctherm.com. I will make note of a few upcoming webinars as well. So we do have one scheduled for October 7th, titled Winning the Heat, the Race Between Electronics and Thermal Interface Materials. So this is actually, we have a guest speaker coming to join us from MG Chemicals to talk about their utilization of these transient techniques in the thermal interface material space. And then later on in October 14th, taking a look at thermal management of tires to improve heat resistance. And again, similarly, we have a guest speaker here from ARDL. I was actually at the Global Polymer Summit conference, saw the speaker give their talk here, and we're doing kind of a little bit of a recap of some of the findings and some of the interesting learnings from that Global Polymer Summit. So we'll be recapping that October 14th. Making note of some upcoming events. Really, this is for folks that maybe if you're in the area or you're planning to go to these conferences, or maybe some of your colleagues were, we'd love to connect, have a conversation if there's interest in doing so. We are currently at the NRW Nano Conference. This is being held in Germany. And then later on, I guess that would be next week, we'll be at the Battery Show North America being held in Detroit. So if you happen to be in the area for either of these events and you'd like to connect, certainly feel free to reach out. We will have representatives at both. And lastly, if any of this was interesting to you guys, maybe you wanted to learn a little bit more, but maybe tailor it a little bit more specific to what you're working on, we do offer free technical consultations where you can meet with someone from our technical team to discuss, your testing and application needs. You can see a live demonstration of how the measurements are actually performed. We have a library of representative materials. We can kind of show everything, everything from materials that are used in composite designs and spaceships to some very, simple clothing apparel wear, depending on what application you're looking in. So definitely feel free. We'd be happy to schedule some of these sessions. If you like what you've seen and maybe you're looking for some budgetary information, requesting a quote, again, we will provide those free of charge. So if you wanted to get a free quote, certainly reach out. And then for our testing services at thermal analysis labs, again, if you're looking to get some testing, but you're not quite ready to bring an instrument in-house, this is just kind of a snapshot of some of the testing services that we offer. If you'd like to go into this a little bit further and kind of, again, get some costing information, happy to do that. My last request is give us a follow on LinkedIn if you're not already doing so. This is where we post all of our latest and greatest content, different application pieces, upcoming webinars. So if you're looking to stay up to date with us and what we're doing, definitely feel free to give that a look. And with that, this brings us to the end of the formal session here today. So for folks that are dropping off at this point, I would just like to say thank you for joining. Appreciate you taking the time. And for those that are sticking around for the Q&A, just give me a few minutes and we'll go into that shortly. But if you're dropping off now, once again, thank you for joining.